Hi, I'm Chen Ji, and today I will introduce you a very innovative and promising quantum computation proposal, which is utilizing the Majorana formulas to exert topological quantum computation. These are the contents I will cover today and try my best to explain. First of all, we need to know that what is Majorana. With the theoretical knowledge, then we go to look at what's the experimental research on it. You may feel how easy it is to publish a paper on Nature or Science. However, I believe till 2018 at least, people still cannot convince themselves they have actually catch the Majoranas in the labs, so it is really difficult. Then, assuming we cheat and we got the real Majoranas in our labs, I will introduce you how it can be applied to quantum computation, which is also how it can meet the DiVincenzo's criteria. At last, I will talk about some ideas both in the frontier researches and also from myself. Okay, let's first move on the theory. The basic idea for Majorana is we can split fermions like electrons by doing the following operations to the creation and annihilation operators. What you can see is C dagger and C is split into gamma 1 and gamma 2, and gamma 1 and gamma 2 is just Majorana operators, which can give us the Majoranas. Quite easy, right? There is a whole bunch of theories behind it, and I did not show here. But if you are interested, you can just look at this website, which is very thorough and very easy to study. Now, if you can accept it, we can just think these are the Majoranas, and we got it. Alright, let's move on. You can see here, they are all paired Majoranas, and actually they are fermions. So when you detect them, you only see the properties of fermion, but not Majoranas. Then, how can we get some Majorana, and at least we can observe in the lab? The answer is we need to unpair them and repair them again. Here is a toy model, the Kitave chain. By doing the operation, we can get two separate Majoranas at the ends of the chain. However, there is no free lunch, and you need to pay a price for it. In physics, that is energy. You can see initially, when they are all paired, the Hamiltonian is just for electrons, where it is related to the chemical potential in the system. After reorganizing them, we only can calculate the paired Majorana energy, assume it is related to the T I show here, which in experiment can be related to the superconducting gap energy. This interesting thing is by manipulating these two parameters, we can get topological behavior. Here you can see when mu equals to minus 2t, direct cone shows up in the energy diagram. By topological protection, the energy diagram will exactly symmetric along the axis E equals to 0. The next question is, how to apply this model into an experiment? Well, the answer is 1D superconducting nanowire. Before that, let's take a look at what we need to prepare Majorana experimentally. First, a system with electrons which has chemical potential mu is needed. Second, we need to introduce a superconducting gap, which is related to T and we just introduced. It is also needed to introduce a particle-Hall symmetry. If you are interested in the details of the particle-Hall symmetry, we call it pH symmetry. You can just take a look at the website I shared before. The third we need is magnetic field, which can introduce Zeeman splitting, and we can distinguish spin-up and spin-down electrons. Spin is something we are interested, but not here. So we need to consider just the spin up or spin down, and where we need to introduce a Zeeman field. And then we need to introduce a spin orbit coupling, which is needed to open a gap here. It's just the gap you can see, at the 3 points, very little gap, but it is needed. All right, even if we have Majoranas experimentally, How do we detect it? The answer from the scientist is 4 pi Josephson effect. It is different from the normal Josephson effect that the period is 4 pi here rather than 2 pi. Then if we turn it into a nanowire, what should we get? Well, for normal superconductors, there will be a gap, existing between the two energies. That's because the parity of the intersection with the axis is even. The intersection will combine, in some sense, these two intersections. And finally, you will get a zero parity because they are all even parity system. And you get the final energy diagram. However, for topological superconductors, what you will see is the intersection stays there because it's an odd parity. And finally, what you look is actually like two energy level close enough to zero and intersects as a high point. Now you can imagine that these two energy levels corresponding to the two ends of the nanowire where the unpaired Majorana locates. The story behind this is very complicated, but what I show here is just a result and a straightforward explanation. However, the physics never give us an easy task. The detection by principle is very easy, but in experiment, they have two enemies. The first is particle poisoning. When you do the measurement, another electron comes in and enter the system, and you will get a different result. What you have is topological, and you are measuring it. You want to measure it very slowly because it is all adiabatic process, and you don't want the system evolve too fast. Another electron comes into the system, it occupies a higher energy. Oops, what you will find, if the original electron you are measuring is here, and it's climb, it should be finally arrive at this point. But another electron come in, and what we will measure is this electron, and oops, it goes to the same point as what you original have. So you think this one is trivial, but actually it is not. The second enemy is the Landau-Zener tunneling. Okay, in this case, we assume what you have is trivial superconductors. And you still goes in this line. This time you want to do it very fast because you don't want quasi-particle poisoning. And what do? You climbs. Oops, at this time it is very close, and it just goes to the higher energy levels because of the tunneling process, and you did it so fast. And the measurement is done in this line, and finally, what you get? All right, it goes to the highest point, and you think, wow, it's a topological one, but actually, it's just a trivial superconductor. All right, here is some real experimental results which are published on Nature of Science. In this paper, the basic structure is metal, topological, superconducting, and metal, this structure. Because of the energy of Majoranas, always zero, because that's what we call it the zero mode. What you measure in the result is that you still get the electron resonance when you apply the zero voltage because it is aligned with a bind diagram. And what do you see? Well, there are still some transport behavior. That's strange, and that is Majorana. And here you can see from the picture C, what they get is you can see the conductance at the 0 point. So they announce that they have the Majoranas. The second one is more clear maybe. He added a quantum dot between the metal and the superconductor. So you can see this energy diagram alignment. The peak at the 0, when VSD equals to 0, there is still conductance. So they also announce that they have the Majoranas. And maybe more clearly, you can see this picture. These two peaks, at VSD does not equals to 0 is energy reflection. but when VSD equals 0, you can see the peaks, and that's a Majoranas. But some other mechanisms also can explain this. So scientific research, they cannot convince themselves that that's exactly the Majoranas. All right, why not we cheat and we say that got the true Majoranas? Then how does this method can do quantum computation? Let us start from the DiVincenzo's criteria. The first is we need a two-level system. It is easy to understand, right? It depends on the parity of the Majorana Fermi mode. You can think if there are not Majoranas, it is 0, and if there are, that's one. The second requirement is not mentioned, but you can imagine by modifying those parameters, you can shift between the 1 and 0. For the decoherence, that's what the topology may make sense here, because for the decoherence, Majorana shows its advantage because the system is under topological protection. Theoretically, local effect on the system is absent. Thus, if we ignore the experimental noise, the system can stand for extremely long time. However, particle poisoning can easily disturb the system and affect the information we read out, which can be a problem. But at least it's much more promising than the normal spin qubit system. The fourth, the universal control gates, are also not mentioned yet, but the next concept about breeding Majorana 0 modes will play the similar effect, and we can talk in the next slide. The last one, the readout capability. Well, we even cannot convince ourselves we actually see the Majoranas. How can we say we have the robust way to read out them? Alright, until now, we have nothing special about Majoranas. How about entanglement? Well, after read this slide, you will find it is quite easy here. Here, assume you have a bunch of Majoranas. Switching between them perform a unitary operation to them, which can be described in matrix. Thus, the sequence of the operation will matter, which cannot happen in bosons or fermions because you just times 1 or minus 1. That's a scalar. The sequence cannot change the final result. Thus, the algorithm we can perform in the Majorana quantum computation system is much more abundant. How to realize them experimentally? Actually, not too hard. Here, between them is a channel. All the Majoranas stay at the bound state. And if you have 3 Majorana pairs, which is 3 qubits, then the breeding is just the answer for entanglement. You can shift this, gamma 2 to the junction to store them and move the gamma 3 to the position of gamma 2 and then, take the gamma 2 back to the position of gamma 3 and then it's done. Then these 2 states are entangled. After the breeding, they still lies on the bound states and the energy are the same. You cannot measure it by energy and tell the difference. Alright, then what about future? Actually, it's a very tricky question because we don't convince ourselves that we actually catch the Majoranas in the labs. They are just like the ghost, which we still cannot see them. Not to mention we need to control them. Some scientists compare it to the 2014 Nobel Prize, Higgs bosons, which are also hard to detect and data sometimes can be explained by other mechanisms. Thus, maybe whenever we have found it, there should be another Nobel Prize in condensed matter physics. The most common system for Majoranas are still topological superconductors. However, another promising idea is that we can also see them in quantum spin hole systems, which are also topological and can connect to Majoranas. Here is a reference I used in this slides. The first is the website I mentioned before, which is a very good topological condensed matter physics learning website. And if you are interested, I think this will help. Thank you so much.